Hi, welcome to another edition of Linear Algebra. Today we are going to have one of many lectures on applications. So the first application we are going to look at would be related to force vectors. We are going to talk about several examples of how linear algebra can be used for handling problems related to forces. So let's go ahead and take a look at this. So you remember that we said there are many things in nature that can be considered similar to vectors in linear algebra. We had, for example, displacements, velocity, acceleration, and force is one such thing. So perhaps one way you're familiar with the concept of force is that you have played a tug of war with your friends or something. So you have some rope and you're at one end and you're pulling on this rope, and somebody else is at the other end, and each of you are pulling this rope toward yourself with a certain kind of force. Well, the winner is going to be decided by the resultant. So if you have one force here and another force here, you want to compare them and see who is going to be the winner. If you are pulling everyone on the other side toward yourself, means the net or the resultant is in your direction. So if you are person A and this is person B, the question is, what would A plus B gonna be? Well, we are gonna have a kind of a stalemate if A and B cancel each other out. In that case, you say what? In that case, you say A plus B is equal to 0. When does that happen? When the two forces are in opposite direction and have the same magnitude. Of course, that doesn't happen all that often. Typically one side is going to win against the other side. The question is, well, what if we have many more forces, more than just two? How can we figure out the resultant in these cases? Think about perhaps a new kind of a game where you have three groups, perhaps each of them trying to pull the rope in their own direction, and say tug of war with three groups. I couldn't think about what would be the regulations for this kind of a situation, but perhaps you, being the engineer, you can come up with practical examples of this. Me, being the mathematician, I can give you a simpler answer in an ideal world. The ideal world here would be, under what circumstances can we say we have an equilibrium? Equilibrium means sum of your forces is 0. Somehow perhaps they have cancelled each other out, and then in that case, if you have, for example, a ring in the middle here, the net force on that ring is going to be 0 and it's not going to move in any direction. However, if the sum is not 0, the ring is going to start to move in that particular direction. So when would it be that the sum of three forces will be 0? Well, aside from tug of war, why would be interested in a problem of that nature? Well, it's a very standard question in the beginning physics or engineering classes when you are talking about forces and such. So toward the end, we are going to look at the following problem. Perhaps you have an object like a painting, and then you're hanging it from a wall by some ropes. So you have a rope number 1 and you have rope number 2, and then you know what's the weight of this object, this painting, what's the total weight of that. So you know the force or the weight of the object. You want to know how much tension there's going to be in these ropes. So you want to know the tension here. Let's call this thing A, and perhaps the tension here let's call this one B. You want to figure out what the tensions would be. Well, why do you want to know the tension? Well, one simple reason, for sure, you don't want the rope to break and your precious painting fall. So there's a safety issue here. You want to know what's the tension rating of your rope, and you want to be secure in that sense. So we are going to look at this problem in two different ways. One of them is going to be a connection to something you saw in high school or in your trig class. There was something called the law of sines. Law of sines. There is a surprise appearance of this concept in this physics problem. Law of sines is a way of solving this type of problem, but we are also going to do it another way that is perhaps more common, by using the components of a force. So first, let's go ahead and look at this issue of components. What's a component of a force? So if you have a force, we have a force F here, and then you want to create that force out of several other forces. For example, you might have some direction, let's call this a red direction, and then the other one, say, blue direction. Your question might be, can I take this force and break it up into two forces, one a red force, one a blue force, such that the two of them together will be equivalent to my black force? Well, it's very simple. You just make your parallelogram. You draw line parallel to the blue line. So I go this one parallel to this, and the other one parallel to the red one. So now I have two forces. One is this, and the other one is this blue force. So I can replace this black force F with the sum of the red and the blue one. Now, these are going to be called components of F along these directions. Typically, the directions we choose are going to be perpendicular to each other. Life is a lot easier if our components are perpendicular. So it's taking the same problem. So here's F. In most applications, we are going to be happier if our axes are just like the X and Y axis. Doesn't have to be, but that just makes our life a bit easier. So we draw X and Y. We still do the same thing as before. I still go ahead and draw parallel to the red one, and then parallel to the blue one. Well, by now you are back to what you have done in many of your classes. You have a point, and then you have the X and Y coordinate of that point. In this situation, however, this is going to signify as the components of F. So these are components of F in X and Y directions. Having them perpendicular makes a lot of basic trigonometry to be available to us. So for example, if this is an angle theta with respect to x-axis, and let's suppose that we are just doing it exactly like in trigonometry, where counterclockwise is considered positive, going from x to y-axis. That's how we measure it, and that is a positive angle theta. Well, let's go ahead and call this one f sub x and this one f sub y. So who is f sub x? F sub x is going to be the magnitude of the vector times what? Times the cosine of this angle. Okay, so cosine is a ratio of adjacent to hypotenuse, and then you can write it like this. How about fy? Well, fy is this is same as that fy, and fy is the hypotenuse times the sine of this. So these basic relationships that you have seen in trigonometry can be used here, and makes life a lot easier. Okay, sometimes you want to go in reverse, that is, these components are given to you and you want to find f. Let's go about it this way. So if I have one component is given to me, or one force is given, let's call this one say A, and the other one, well, let's consider this one to be B. What is the resultant in this case? The resultant, well, let me draw it better. The resultant is F. You can write it in a number of ways. You can write it with A and B. You can write it AI plus BJ. We said you have to be careful how you enter these things in the software. So typically they ask you to choose boldface for A and J, I and J. Well, what are the relationships? First of all, the magnitude. Magnitude, well, very simple. That's the Pythagorean theorem. Magnitude is sum of the squares of these two. How about the angle? Well, you decide what angle you want. So perhaps we go after this standard angle here. One of the ways of handling this thing is to say, for example, tangent of theta. Tangent of theta is the opposite over the hypotenuse, actually opposite over adjacent, and you go ahead and find the angle itself with the arctangent, and you make sure that you are careful there with respect to which quadrant you are supposed to be. So when you have two forces, the situation is very simple. You just need to be absolutely sure about the physical setup of the problem. That is typically a lot more significant than the formulas that are involved there. You have to read the problem very carefully and make sure you understand the details. Okay, so let's go after the three-force problem. What if we have three pieces to our problem and we want to work with that? Okay, you come across this problem probably in your physics class, your engineering class. Let me show you some setup that you might have seen, perhaps even in high school. Okay, so there is something called the force table. Force table kind of looks like a stool, actually. It's round. There's a pin in the middle and a ring. There are these pulleys on the side, and then you pass a rope from that ring over the pulley, and then you attach some weights to these threads or ropes, and then you can figure out the position of your forces by moving these pulleys around. The edge of this table is graded, so you can figure out at what angle you're positioning some force, and there you could have several forces on this table. Simplest example, there would be three of them. So here, like this, in this case, there are three of them. Having two would be the simplest. It's like a trivial, not very interesting. The two forces have to be opposite each other, and you have to have same weight on them. At any rate, you make sure that this ring is in the middle so that you'll be able to read the angles, and it has to be stationary so that you know that the forces have cancelled each other out. And then you want to, well, investigate what's the relationship between the weights that you have and the angles that they have to be at for them to cancel each other out. So that's a problem that we are going to look at. Again, we are going to go back to that example of, say, hanging a picture frame from the wall or something, and I'm going to do one version of it. You're going to do another version from your textbook. Okay, let me go ahead and show you another demonstration. So here is a demonstration on Desmos. Here we have three forces: the green force, the red force, and then the blue force. The sum of these three forces is this purple force. You see, here's the purple force is quite substantial, meaning if I have this green, red, and blue, and if I take all of them and replace them by this purple is going to do the job of all three of them. Well, what if I want to do a tug of war situation and I want these three forces to cancel each other out? Of course, they cannot be in this kind of a position, because in this way, well, they point all in the opposite direction. So I have to play with at least one of these things to make the net force to be zero. So let me just pick this up. So you notice that I am lessening the sum by bringing it to this side. Let me just move this in the middle a bit. So if this blue force increases, here it almost cancels the other two, and by now it did. Okay, so this blue, green, and red are in equilibrium because their sum becomes zero. We are going to take a look at this thing mathematically and then try to analyze it by some simple linear algebra. Let's go see how we do that. Okay, the question we are investigating is, well, if I want three forces to cancel each other out, what do I need to observe? Well, suppose we draw these forces just like what I had over there. Suppose this is my A, and this is my B, and this is my C. How would I investigate if the sum of them is equal to zero? We have two ways. One is by geometry, and the other one is by algebra. Geometry, we draw pictures and analyze that. Algebra, we are going to have components in setting up equations and making sure our equations zeros on the other side. So let's first do by geometry. It's kind of more close to what actually you see out there. Well, if I have three forces and I want the sum to be, I want to investigate the sum, I just go ahead and draw one of them. So suppose this is a copy of A. So I just take this thing and copy it here, and then I copy B. So maybe I color them same way. So this is supposed to be my A, and then suppose this is my B. So I try to go parallel to that. So this is my B. Let's say this is my B, and then I have my C. So from this point I draw my C. So if I draw C and say I come here, what would I say the sum of these three forces is? Red, blue, and green. Well, the sum is going to be from starting point of the first to the ending point of the last. This is what A plus B plus C is going to be. So A plus B plus C. We just draw these forces that we have one after the other, and then from beginning of the first to the end of the last, that's going to be the sum. Well, if you want the sum to be zero, then the beginning point better be same as the last point, which means if the sum of three forces is zero, then they have to form a triangle. So here's our first discovery, that if I have three forces canceling each other out, then when I draw them, they have to make a triangle where the tip of the very last one should touch to the beginning of the very first one. That's true for any number of forces. If you draw them in this fashion, the last point should be the first point for the sum to be zero. So in this case, we say A plus B plus C is equal to zero. Okay, that's one major discoveries. Second thing, we said this problem has something to do with law of sines that you have seen in trigonometry or perhaps in high school. Let's go ahead, investigate that, and that's going to give us a very simple way of doing some of these problems. But as we said, in general, the more professional way of doing stuff is by coordinates and components and such. So let's go ahead and take a look at this. I have a triangle here, and I had my forces drawn, a so-called three-force diagram is in this way. The first question is, how do the angles relate to each other? So for example, here I have some angle. Let's color it. So I'm going from A to B. That's an angle here. How do I see that angle in this triangle I have drawn? If you extend A, okay, now from this extension to B will be same as this yellow angle I drew over there. So the rotation from A to B here is that yellow angle. Here I see it exhibited in this way. So the interior angle, that typically that's what you deal with when you are handling some problems in trigonometry and such. This is going to be supplement of that. So for example, if this is say 110 degrees, that's going to be 70 degrees, so that the sum becomes 180. So the angles here between A and B, B and C and A are supplements of the angles that you see you typically work with inside triangle. No problem, nothing's going to go wrong if you use the exterior angle, but that's the same. Okay. So the connection between our picture here and the picture there is just what we described. Now, how does this relate to high school trigonometry? In high school trigonometry, you remember that if you have a triangle and the length of the three sides, if you call them say A, B, and C, and the angles, perhaps you call them alpha and say beta and say gamma, what was the relationship between these three? Let me see if you can pause this thing for a second. So that was our deal, that you pause and try to answer some of these questions. What was the law of sines? Do you remember what the law was? Okay, so if you have it, that's great. If not, let me perhaps ring some bells. It was A divided by what? What was in the denominator? Of course, sine of the angle opposite to that side is equal to B divided by sine of well, beta we called it here, and C divided by sine of the angle in front of that one. Okay, so this is a simple form of law of sines, a more advanced form of it. There's also something which is equal to all three of them, but let's put that aside for now. So what's the application here? A, B, C are the magnitude of the forces. Okay, the length of these arrows are the magnitude of the forces. So it's going to be magnitude of force A, magnitude of force B, magnitude of force C. These angles will be, well, the angle opposite of those sides. You could use interior or exterior angle is the same, because the sine of these two happens to be the same quantity. So you can use this, you can use that, it's all the same. Okay, let's do a simple exercise related to this. So I'm gonna draw a configuration a bit different from what's in the text, and then you go ahead and read the text also, and that would be an additional example for you. So suppose we have an object attached to a nail on the wall with two ropes. So I have a rope here, and I have another rope here, and we have managed to balance some big painting so that it stays the edge of it staying horizontal here, and then we go ahead and measure at the end that well, how are these ropes sitting here. Suppose in our measurement this turns out to be 40 degrees and this turns out to be say 25 degrees or something, and the painting or a mirror or whatever it is, let's say it is, let's say everything is a 50 pounds object. Okay, so here is our precious painting or mirror, and here there are two ropes. Well, of course these ropes are pulling on the sides, on these corners, or wherever they are attached to the nails or something, and of course they are going to be pulling on that nail on the wall as well. So here there is some force. Let me just abbreviate it by calling it force A, and here's going to be another force. Let's call this thing force B. Well, the question is, what are tensions A and B? Of course they depend on how heavy this object is. Double the force, these are going to double. It's also going to depend on what angles you have here at the end. So A and B, the tensions are going to depend on all these numbers that we have. So find the magnitude of force in each rope, or find the tension A and B. What is A and B? Well, let's consider this thing as the this is the weight, so let's call that one W. So if this painting is not falling or anything, it's sum of the forces on this painting has to be 0. A plus B plus W has to be equal to 0. We call that equilibrium. If things are not falling, it must be that the total force is equal to 0. Well, now the question is, if I know W, so I know W to be 50 pounds, how do I figure out A and B? Well, two ways of approaching this thing. We say, well, let's do law of sines first. Well, in these problems, the main thing is to draw your triangle carefully and figure out what are the angles between the sides. So if I have my W here, so I have the W, and then I have my A, so presumably say this is A, well maybe it has to be bigger than that, A, and then B, this is, let me write it better so that sorry, so that it doesn't run into each other. So let's A and W, and well, we said if nothing is moving or nothing is falling, that the third force has to come back where the first one started. That's the condition. Well, the only thing left is to figure out what are these angles. Okay, so you have to use some basic geometry to find your angles, and then you're all done. You have many choices for here, just be steady and consistent. So W and A. So here I copied the W on the side. So well, what is this angle? Well, this is 40. It's called alternate interior. This is also going to be 40, and this is a right angle here that's 90. So this whole thing is 130. Another way of looking at it, between W drawn here and A, this angle is going to be how much now? Okay, so if this is 40, what's that going to be? That's, of course, it's going to be 50. So this angle is simply the complement of that angle. In this drawing, that's 40, and that's going to be 50. By the similar reasoning, if this is 25, you tell me what's the angle up here. If this is 25, what would be the angle here? So again, here is a simple drawing I can do. Complementary angle here is going to be, let me write it outside, this is 50, and so this is going to be complement of 25. That's going to be, of course, 65. How about this angle? Several ways of doing this thing. So this is 50 and this is 65, and the third one is going to be 180 minus 50, 65. The three of them have to add up to 180, so you can figure out the third one. So that's going to be 115, and that's going to be 65, which is unfortunate coincidence. This angle is going to be the sum of these two, so this is going to be 40. So let me write these things. So this 90 minus 40, this becomes 50. This is 90 minus 25, 65. This is 40 plus 25. This is 40 plus 25, or 180 minus 50 plus 65. Okay, and what is next? So the main issue is to figure out these three angles. So again, just remember, in our drawing, these two angles are complementary, these two angles are again complementary, and the third one is the sum of these two angles. One force is given to us, and that is the weight of this is 50 pounds. So we are going to write, let me write it like this: W divided by, let's we said this is sine of 65 is equal to A divided by sine of 65. That's equal to B divided by sine of 50. Well, these quantities you can figure out from the calculator, and W, you know what that one is. So in this case, the weight is given as 50 pounds, so I can figure out what W is going to be 50 pounds, and then I can figure out what the A is going to be. In this case, by coincidence, the denominators are the same, so the absolute value of A is same as the absolute value of W, and that's going to be 50. And B is going to be, where we cross multiply weight of the object times sine of 50 divided by sine of 65. Use your calculator and then round it to as many decimal places as the problem asks you to write it down. Okay, so this is one way of handling this problem. What's another way of handling? The other way of handling this problem is by using components. So using components, we draw our XY coordinate system. We still have to draw everything again as before. So let me maybe I copy this thing in red. So I have my red force here. This is W. So that was 50, and then we had called the left one A. So I'm going to draw A perhaps in blue, and it's drawn at the angle of 40. So that's the important thing here, to draw this thing at to remember what angle it's at. So this was 40 and this was our A, and then the other one was B, and that one is angle of 25 here. So component version of this thing, we say the vector W plus vector A plus vector B, this is our vector B, have to be adding up to 0. If sum of several vectors is 0, then any components of them that you consider, that's going to be 0 as well. That is, if I have the x component of W plus the x component of A plus the x component of B, that will be 0. So this means the x component of these things. Well, what's the x component of W? Well, W doesn't have any x component. X component of A, we talked about components, it would mean this one. X component of B, we have to, well, figure out this one. So they have to add up to 0. The W doesn't have an x component because it's already vertical itself. So the blue and green, of course, have to cancel each other on the horizontal direction. How about the vertical direction? Well, we take the y component of A and then y component of B. Okay, the blue and the green one, the two of them should cancel the red, and then we are all set. So the other formula is that the y component of W and the y component of A and the y component of B has to be 0. So in this style, we resolve into components, use the trigonometry to do that, and then write our equations and figure out the pieces, and then figure out A and B. Okay. First equation, W doesn't have an x component, so I just write 0 anyway. AX, what's AX? AX is going to be length of A. We said to find the horizontal component, you have to multiply by that cosine of 40. How about B? The x component of B, we see is negative here, going in this direction, or if you want to be more careful, use your angle from x-axis, and that will automatically tell you you have to have negative. So here I write minus B, and that's going to be cosine of 25 equal to 0. Okay, so alternative way of doing this one would be to measure this angle, which is 155, take the cosine of that, which is minus cosine of 25. That's fine. Well, W in the direction, W in the y direction is going to be our weight, except that it's pointing down, so it's going to be minus 50 plus vertical component of the blue vector. So how do you figure out vertical component? Well, the opposite is going to be measured by sine. So I'm going to have A times sine of 40. How about the green one? The vertical component of the green is going to be B times sine of 25. So this is our system of equation that we have to solve. Solve it for what? Solve it for the tensions A and B. How about the rest of these things? Well, these are numbers. Sine of 25, cosine of 25, and whatever else we got here. These are things that on your calculator turns out to be some number, whatever they are. It's better to leave it like this, because those numbers on calculator aren't friendly numbers. You write it, you regret you wrote them. So better just leave it like this and get used to having numbers being represented by values of functions. This might feel a little bit unnatural to you. Your tendency would be, oh, just jump to the calculator, convert this thing to some decimal, but then you typically make some mistake on decimals, and then later on you lose track of what that number meant. But if you leave it like this, things are a lot more descriptive. Well, what do we do with this system? Well, first of all, this is an example of linear algebra. This is a system of equation to consider, to solve. Later on, we're going to look at much bigger system, but you have seen this is a 2x2 system. We have two equations and two unknown quantities. So that is something you have seen in college algebra and such. You should be able to handle that. We write the first equation, a cosine of 40 is equal to b cosine of 25. So we are choosing to use a substitution. I find one of these quantities from one of the equations, substituting the other equation. This is one of the standard ways of solving these things. The other one is elimination. You could do that one just as well as you're doing this one. So here I get a is b times cosine of 25 over cosine of 40. In the next equation says a sine of 40 plus b sine of 25. Let me take the 50 to the other side. Is equal to 50. So I'm going to take this a here and substitute for the a here. So I'll get b times cosine of 25 over cosine of 40, then times sine of 45, sine of 40, plus b times sine of 25. The whole thing has to be equal to 50. Okay, this might look a little bit crowded for you, but again, remember, these are just all numbers. You're after b. So if I take a absolute value of b as a common factor, everything else is going to go inside a parenthesis. So it becomes cosine of 25, cosine of 40, sine of 40, plus sine of 25. That whole thing is equal to 50. Well, how do I find magnitude of b? So I have to cross multiply. Maybe I go ahead and take a common denominator so it looks a little bit cleaner that way. So let's go ahead and take a common denominator. So I get cosine of 40. Numerator is cosine of 25 sine of 40 plus sine of 25 cosine of 40. That whole thing is equal to 50. Well, now we are ready. So b is equal to 50 times this denominator. It becomes cosine of 40 goes here, and then I have cosine of 25 sine of 40 plus sine of 25 cosine of 40. The magnitude that I was after for the force b, I can find it like this, and I can find a just as easily as I found b. Before we leave this problem out like this, you might feel a little bit uneasy that you told me b is equal to this, and now you're writing something that looks quite a bit different. How's that? Well, let me take you back to your trig class. Do you remember anything looking like the item in the denominator? Let me give these things some names, and let's see if that ring a bell for you. If you had something like sine of alpha, cosine of beta, plus cosine of alpha, sine of beta. Do you remember from trig class what that thing was? I have sine of alpha, cosine of beta, and then cosine of alpha, sine of beta. What is that? Yen, maybe you want to scratch your head for a second and then be sure of what your answer is. Did that ring a bell for you? What was it? Well, that is of course our famous sum of angle formulas. Sine of alpha plus beta is equal to this. So this is really cosine of 40 divided by sine of, well, 25 plus 60. So this is another way of writing this. 50 cosine of 40, denominator is sine of 65. So we came closer to the answer that we had here before. We have a sine of 65 in the denominator here. You might raise a second objection. How come this is sine of 50 and then here I have cosine of 40? Let me ask you, sine of 50 we had over there, and here we have cosine of 40. What's the relationship between them? Of course they are equal to each other. If you have sine of an angle, that's equal to the cosine of the complement of that angle. Okay, another formula from trigonometry. So in fact it's perfectly okay to write it this way or write it as sine of 50 over sine of 65. So you notice several things. One is the role of trigonometry you had in high school in analysis of what we had here. So we saw several examples where math that we have done comes in and explains to us forces in nature. The other thing we learned here is that you remember I insisted that do not convert these things to decimal on your calculator, because if you do, by the time you come here it would be essentially unrecognizable as to what these things are. It's just a jumble of numbers. But when you write it in terms of the functional equivalent of it, there is a hope that you can remember something from other areas of mathematics and help yourself clean out the expressions and such. Okay, so this is an example of how to solve these problems. You might say, well, the second one took quite a bit longer than the first approach that we had here, but you are going to be asked to do this component analysis in pretty much all of your engineering classes, so you want to get used to it. And also I want to insist that you also go ahead and read the textbook version of this problem, where the way we are hanging the object from the wall or ceiling or something is to pull a rope in these two directions and then have this attached to our object in this way. Well, you can debate advantages and disadvantages of either of them, but be prepared for either of the two approaches, and then you want to read this one in your text, section 1.4, page 50, I guess 2, and then you'll be ready for the problems of that type. So simple ideas, but you need to practice it and make sure you go through the process several times to be able to handle problems in this section. Okay, until next time, good luck and God bless.